All right, so good afternoon, everyone. Again, so let's get started. So I want to this. I would like to start to give a overview. This lecture to be a kind of overview lecture, as I said earlier, so that all of us will be on the same page and we can move forward together. So we'll start here. So we have a real world problem that you would like to solve. Have a real world problem you would like to solve. And so this real world problem could be, like for example, managing your exam. Like for example, so you all came from this JEE exam, and so you have written exam in different test centers, and you would have got different marks in maths, physics, chemistry, and you rank them, you compute percentiles, all those things. There is a certain real world problem that is there, and you would like to come up with a software system which completely models solves the problem at hand. Or it could be like, for example, the current COVID pandemic, and you know uh, so you want to know what are the states in which there is a high incidence of COVID, or what are the states in which the growth is rapid in the last 1 month, and yeah, like that. Or you want to analyze IPL statistics, or you want to analyze Premier League football statistics. So there are different, or you want to build a weather model which predicts the path in which the cyclone will take, no, a low pressure area will take. So you have different real world problems at hand. You have different real world problems at hand. And so in order to solve these problems, you need to come up with a representation for this. You need to build a computational model for these problems. So you need to build a computational model for these problems. Right? And when we kind of build a computational model, there are two parts to it. One is representation structure, representation. Yeah, I have less space here. Actually, let me do. Sorry, should use a bigger thing. So you have your real world problems, and we want to build a computational model for these real world problems. And there are two parts to this computational model. One is representation structure. And other is algorithmic. So once you represent the problem at hand in some suitable way, you would like to do some analysis on that representation structure. So here comes algorithms, algorithmic thinking, algorithmic thinking. So when you are trying to come up with a representation structure, it depends on what kind of algorithms that you want to apply on those representation structure. And when you are designing algorithms, the kind of algorithms that we design, it depends on what kind of representation structure that we use. So it goes both ways. There's a mutual dependence between them. And once we have this model, computational model, then what do we do? So we build a software. We build a software program software. What is software? It's a collection of programs. So we build software for the same, or programs. It's a collection of programs. And when we write these programs, so we use high-level programming languages such as C, C++, Java, Python. What we have many programming languages using which we can write our programs. So here there is one interesting uh, idea, one important idea which you will appreciate later on, not much now, is when we are trying to come up with this computational model, representation structures, algorithms, etc. There are different approaches we can take. Like, for example, we can capture the real world problem as using what is called as an object-oriented design approach. That is, we look at the problems that we take the real world problem and we think of the entities that are present in the real world as different objects, and these objects, they interface with each other in well-defined way. So this is what is called as an object-oriented design approach. So if you take an object-oriented design approach, then you may have to use programming languages such as C++ and Java, which supports encoding those ideas nicely. But if you use a different approach where you take, hey, this is a big problem, we divide this problem into multiple problems, and each of these problems are further divided into multiple problems. This is a functional approach where you take the big problem, divide it into multiple modules. Each module is further divided into submodules. If you take such an approach, then probably you can use C programming language to solve those problems. And then finally, so you have your software, which is written in high-level programming languages, and you have to map this into assembly or machine code. Assembly or machine code. Because all these high-level programming languages, whatever programs you have written, we write in this programming languages, your processor does not understand, because the language in which the processor speaks, the language which the processor understands is different. So here we rely on system software tools such as compilers, linkers, etc., to map our uh, programs written in high-level programming languages into low-level machine code, right? So here in this context, I have a question for you. Let's say if you take a program, this is usually when we have, uh, so you have your program fun.c or hello.c program. So where is this hello.c program residing? Where is this hello.c program residing? And what is present in this? What is present in this hello.c program? And where is it residing? It is present on the hard disk. It is present on the hard disk. It is what is called as a persistent storage, because even if you switch off your computer and boot it up, the program that you have written is still present on the hard disk. And let's say, yeah, so it is present on the hard disk. What is the format of the file? What is the format of the file? It's a .c file, but what does it contain? It contains source code, compiled source code, normal text. Good. Yeah, so all these are reasonable answers. Um, so it contains text, it contains source code. So your source code is in text, it is an ASCII text, right? Like for example, here, if you see cat, there is one program cat pun.cd. So this is a program, so which which contains a printf statement to print something onto the screen. File pun.c. So if you check what is the file type, it says it's a C source code. How does file knows that it's the file command knows that it's a C source code? Because of the extension, and the file contains an ASCII text, because each your C program is a sequence of characters, and each character is encoded in what is called as an ASCII format. Every character is represented using 8 bits. Are you with me? So every character requires 1 byte, and 1 byte is 8 bits. So your C program is a sequence of ASCII characters, and that is what is stored in pun.c, and pun.c is present on your hard disk. So you're all with me here? And so your C program, your processor cannot understand. The language which your processor understands is something different. It understands what is called as a machine code. So we have to rely on this compiler tool. We have to rely on this compiler tool in order to generate an executable file. So I have two questions for you. So now that we have compiled our program, so did your program run? What is, first question is, what is present in pun? What is present in the file pun? What is present? It's a binary file. It's an executable code. It's .exe. It's executable. Assembly language translation. Assembly code. Machine code. So what's the difference between assembly code and machine code? Isn't it machine code binary? Okay, so you have all these nice answers. I think you're all in the right thinking. So what happens is, if you do gcc pun.c minus s, yeah, so Agrim has got it right. So if you compile pun.c using minus s option, then you have this thing. So Control O, let's do this. This is pun.c. Pun.s, this is the assembly code associated with pun.s. You don't try to understand this assembly code. Yeah, but this is meant for our consumption. The processor cannot understand this push queue, move queue, all these things your processor cannot understand. So what your processor can understand is gcc minus g pun.c minus open. I'm just reviewing these ideas. I know many, you know all this stuff before. So if you see this, yeah. So Pun.dmp. Okay, anyways. So the idea here is, if you see each of these, this printf, this is what you have to see. So the LEAA, call queue, these are assembly language instructions, but the equivalent machine code for them, is this. These are assembly language instructions which we can understand, but this is the code which the processor understands, and this is what is present in your executable file. Are you with me here? This is not present in the executable file. When you disassemble this, we get from here we got this. But this is not, this column is not present in your executable file. What is present is this, these are the things that are present in your executable file. So as Agrim rightly said, assembly is in human readable format of machine code, which is binary. And in fact, this is 48-8D, this is hexadecimal representation, but actually the bit representation of this will be loaded into the memory. Dot dump, I just use it some extension. Yeah, don't worry about it. Are you all with me here? Are you all with me here? Don't worry again about hexadecimal representation. We'll talk about hexadecimal representation later. All I'm trying to tell is from pun.c, so this is present on the file system, and so pun.c, this is present on the file system, and you generated pun, which is executable. The executable, this contains machine code, and in between, between machine code and pun.c, we have the assembly code that is primarily meant for human readability, but because this column the processor doesn't understand. When the processor looks at push, it doesn't make any sense for it. But if it looks at 55, it knows it means that it has to do push something. Okay, so this is what it is. And where is pun present? Pun is present on the hard disk. So now if you want to run this, if you want to execute this program, what should we do? So if you want to execute this program, so all you have to do is do pun, and then the program gets executed. So here, if we go back to our this picture, so you are in this picture, I would like to highlight few things. This is the most important idea. So your fundamentals should be straight, and your pun.c is present on the hard disk, and your executable pun is also present in the hard disk, right? And you have generated your pun from GCC by using this command -o pun. This is what we did. And then we have our CPU here. This is our CPU. And then we have the processor here. This is the main memory. This is the RAM main memory. So when we gave our program for execution here as $/pun, so this pun program gets loaded into this pun program gets loaded into the main memory. This is what happens. And then the program starts executing. So like for example, on your machine, Chrome browser icon could be there. So your Chrome browser, the instructions associated with your Chrome browser program is present on the hard disk, but when you double click on it, the instructions of that present on the hard disk will be loaded into the memory, and the program starts executing. Similarly, the Zoom, the instructions associated with the Zoom program, they are present on the hard disk, but when you double click on it, what happens is the instructions will be loaded from the hard disk to the memory, and your Zoom program starts working. Okay. Are you all with me here so far? This is the first revision, review 1. Okay. This is all review. I hope you're all with me here. 2 participants raising their hands. Let's see.
Sir, my doubt is that you did file pun.c, right? And that showed
Okay.
you what was the in what language it was, and what was the contents of it, right?
Yeah, that's true.
So if you say file and say zoom.exe or something like that,
Okay.
what will it give?
Yeah, let's see. Yeah. Yeah, one more question, Vitish. Sorry. So, Vitish, can you raise your hand again? I think I accidentally yeah. Yes, Vitish.
Yes, sir. Like I had a doubt. This you said assembly code is in binary, right?
Assembly code is in binary, na? What do you mean by that?
Like I didn't understand, sir. Like you said assembly code is in binary format. Like in a chat, someone said use the word binary, and you said it's right.
Yeah, usually not assembly code. Your pun is in binary format. Pun is your executable file. It is
Yes,
in,
sir.
we call it as in a binary format. Yeah.
Yes, sir. So pun is in the like assembly code is converted to the binary code, right? In the
Yeah,
executable.
that's true. That's
Yes,
what
sir.
pun contains.
Yeah. So like the source code is in which format, right? Like it is in
It
ASCII.
is in ASCII text, no? It is
Okay.
in text format.
Yes, sir. So what is in assembly code is in which format?
Assembly code, it will just be considered as text, because if you open the assembly code, it will be just a sequence of ASCII characters there.
Okay, sir. Yes,
Yeah.
sir. Understood, sir.
So, Srijan, did you see, like when we did file pun? So this is what it says, that pun is an executable file, and it is in a particular format called as ELF format. These executable files. If you do similar thing in Windows, you will get some other format maybe, but on Linux, executable files, they have this format, ELF format, and it says it is in ELF format, and there is bunch of other information also present. Like for example, one more interesting thing that you want to look at is it follows the instructions present in this file. They follow x86-64 instruction set architecture. That is Intel processors. All Intel processors support x86-64 instruction set architecture. That's a language which all Intel processors understand. And there are AMD processors also which can understand the same instruction set architecture. All right. So now with this as the background, so now what I would like you to see is, let's take a look at this. So are you able to see this, the picture? So if you take any program, if you take any program, so that program, so this is what is called as a flowchart representation for a program. Any program pretty much you can represent. Yeah, so any program, if you see, what happens is, so you start the program and then you read some input, you process the input, and then you generate some input output in that process, and you print it in that process. So this is the high level picture of what happens in any typical computational process. You read input and you process it, and then you print output. So given a problem, you need to know, you need to see what is the input to that problem, and what is the required output. And in order to transform that input to that output, what should you do in the middle? What type of computations that you have to do uh, is what you have to see. So this clarity of thought should be there. So because when we are learning these programming languages, no, like we are lost in the details associated with the programming languages. But what we would like to see is what is the big picture. Okay, what is the input? What is the output? and what computational process that we need to carry out to transform that input, the given input, into output. So once we have this clarity, like so far you studied about, in the last few classes, you studied about how to read input. Like for example, one way of reading input in C is using the scanf statement. You can read from files also using a variant of scanf statement. Like for example, later on we will study what is called as an fscanf statement, using which we can read stuff from files. Similarly, in order to print output, so you use printf, and so if you want to print two files, we can use what is called as an fprintf. And there are lots of nuances in using scanf and printf. Uh, so lot of times I see we get confused there in how to use scanf, how to use printf, and lose sight of the big picture, right? So I want you to understand this thing, that in the big scheme of things, you need to see what is input, what is output, how do you read, how do you print, and any details on how scanf works, how printf works. They are details, and you can use a textbook or use, like for example, you got a doubt on how scanf works, you just do a man scanf, and you want to know. Or you want to know, like for example, the question is what is fscanf? There's a question, so we didn't discuss about fscanf, but all you have to do is you just do man fscanf or look at the textbook. No, it will kind of tell you what fscanf is about, for example. Similarly, if you want to know about fprintf, or so there's no man page for okay. You can just do man fprintf, and you know about printf, fprintf, dprintf, all these things. You'll get a whole bunch of stuff. But these are all the details, okay? These are all the details. These details you can look and read in the textbook, read in the manuals, Google, and do all those things. These are important. We'll go through them in the class, but always keep in mind the big picture. Here's the big picture. So now when we come to computing, so this input that we have, that we read, the input that we read, so we will we will store this input in some format. Okay, so in order to uh, so data storage, you read the input, we have to store somewhere. So the language provides from primitive data types. So now comes this part. So just focus here. So the language provides primitive data types. And then later on, we will see that we can have new data types, user-defined data types also. And the language also provides mechanisms to define our own data types, user-defined data types. It is possible to define our own data types, where these user-defined data types are obtained by putting these primitive data types in some nice fashion. User-defined data types. All right. So let's say if you see the kind of data that we face in practice, like for example, if we are working with integers, and so what kind of primitive data types are supported, are there in C to represent integers? What is the data that is there in C to support integers? So int, so my pen is not visible. I thought I'm using this pen throughout, no one complained. Yeah, because if I use a bigger font, then it doesn't look good. So that's the reason I'm choosing this. So if you look at the integers, there are, like there are two C provides, like for example, either you can use int or you can use, long int, for example. And then you can use, like for example, signed integers and you can use unsigned integers. Similarly, long int also you have signed and unsigned long int. So using these data types, you will be able to represent able to solve a large class of problems. But later on, you will see when you work with when you are working with in the domain of cryptography, there when you work with integers, the size of integers there is so large that these primitive data types will not be sufficient for us. So we have to create our own data types when we are working with cryptography, for example. Yeah, thanks, Shantanu. So similarly, if you look at, if we are working with real numbers, so in real numbers, you have, like, for example, you have float, you have double, and using these representations, or maybe there is long double, I don't know. So using these representations, you will be able to handle a class of problems. But sometimes if these are not sufficient, then we have to define our own data types. And then there is char, which takes care of text, for example. And then, so we have these primitive data types, and then you can think of arrays, array of integers, array of characters, no, array of floating point numbers, array of double numbers, etc. So using these arrays, you can do many other interesting stuff. And then later on, we will also see what are called as structures. So the point I'm trying to get to here is, so the language provides a certain primitive data types, and we can define our own user-defined data types depending upon the necessity, which we will see later on. So we represent the data, and we need to, and using the available data types, number one. And then once we have the data represented, what do we do? So we would like to do computations on the data. We like to do computations on the data. So that is the next part. So primitive. So what all the operators that are present? What operators that are present? Okay. So what operators are present? Like for example, you can have addition, subtraction, multiplication, so on and so forth. So these are some operators that are present. And these operators they are defined on primitive data types. And so when we are working with operators, so there are a couple of things that we learn. Like for example, if you have something like a plus b star c, how do you compute this a plus b star c? So there are two ways of computing this a plus b star c. One way of computing this a plus b star c is a. So this is one approach. So other approach is a plus b star c. Which one is right between these two? So this is what is called as an expression tree. So the first one is true. This is the right. So you need to worry about precedence. You need to worry about precedence. So I know you studied all these things. So I will review all these things and then we will move on. This is precedence. And then if we have, let's say, a plus b plus c, again, there are two ways of doing this. One is c plus a, b, and other is, uh, again, between these two, which one is the right one? The first one. Both are correct. Huh? No, no, in C programming language, this is the right one. This is what is called as a left associativity, left associative property. In C programming language, for example, this is the way it is computed. And in fact, just A plus B, these two are not equivalent to each other. Later, you will see that when you are working with floating point numbers, so this one and this one, the values provided by these two, they are not the same when we are working with the floating point numbers. The order in which we add, it will have an impact on the values produced by a slight amount. And it can have some important repercussions. But this is what is the semantics given by the C programming language. If it is A plus B plus C, then we do the computation from left to right. And then after that, one more thing is typecasting, right? So how does typecasting works? So what is typecasting? So like, for example, if you have something like A plus, no, A plus FB, so where A is an integer and FB is a float, so the underlying processor cannot add a integer to a floating point number because the representation of integers and the representation of floating point numbers is different. So what happens is this one, if you take a tree representation of this, it will be like this. So what happens is your compiler, GCC compiler, it translates this into this form, into float A and then FB. So this is what is called as a typecasting. So the integer variable A got typecasted into a float, and then this and then the addition happens. Are you with me here so far till this point? You're all following? Any problems? So typecasting is very simple. So this, if you look at this picture, this is the simplest way. When you do A plus FB, A is an integer and FB is a floating point number. The underlying representation for an integer and the underlying representation for float is different. So you cannot add an integer to a float just like that. You cannot add 1 plus 2.3 because no, the underlying circuitry cannot take an integer and a floating point number to add. So what happens is your integer is typecasted. So you can see if A is equal to, for example, this is 2.3, and if A is equal to 1, so the value associated with this will be 1.0. That is, a floating point representation of 1 will be different from just 1 than an integer representation of 1. And then 1.0 plus 2.3 will be 3.3. That's what you get. Are you with me here? Does it make sense? So if you have something like FC is equal to A plus FB, what happens is, so TFA is a temporary variable. So int to float, a kind of operator will be applied on A, and then we will see FC is equal to TFA plus FB. This is what happens. TFA is temporary. Compiler auto internally does it. It's not visible to us. So, but let's say instead of FC here, if you have C is equal to A plus FB, where C is an integer variable. If C is an integer variable, then what happens is, so you have A plus FB, all this happens, and then you'll have C is equal to float to int no, FC. Because floating point number, you want to translate it into an integer. So let's say, for example, if the value that we get here is 3.3, then this 3.3 will be truncated and you get a C contains 3. This is a casting from float to int. Are you with me on the typecasting? So in the other class, there is an interesting question. So is there a loss of information as we move from this 3.3? Uh, so this idea is simple. So if you have floating point number 3.3 and if you want to assign it to an integer, the fractional part will be ignored and the integral representation, the integer representation of the integral part 3 will be present. So what I want you to understand is the representation of 3.2 and 3 are different. 3.0 will be represented in a different format as a floating point number, but 3 will be represented in a different format. So what happens is this point 3 will be dropped and this integer will be represented uh, in the variable c if c is an integer. Are you with me, Anish? Okay, great. So now, what's the story? Yeah. So now there is this question. Hey, when we are moving from no float to int, isn't there a loss of information? See, when we moved from 3 to float, it became 3.0. You are kind of all right. But when we moved from 3.3 to 3, then this fractional part is lost. So is there there's a loss of information, right? So is it a good thing or bad thing for you? So is it a good thing or bad thing? Is it all right to lose? Yeah, so losing out seems to be bad, right? So this Vishwateja says no. Why is it not a bad thing, Vishwateja? Losing out. Float and int have the same size, but no, float represents a large space of numbers than int. Yeah, why is it bad, Vishwateja? Oh, you are saying it is bad. Huh? Oh, you said that. So Anirudh, so although float and int may have the same size, but the range of numbers represented by float is very high when compared with int. So Anish has this question depending on where you are using it, right? So yeah, can you give me an example of where it is all right? The memory occupied will be the same. Yeah, that's true. So one place where it could be, like when you take a camera and you take a photo, every pixel is represented using three components, red RGB components. And each of these components, they will be present in the range, 0 to 255. So if you want to compute a gray pixel, so if you want to take a color image and you want to compute a gray pixel, so usually you take something like zero point 0.6 times the red pixel plus 0.4 times some green plus 0.7 times blue, something like this we do. So when we do this, what happens? So here, and the gray pixel should also lie in the range 0 to 255. So here, when you do the truncation, it is all right. The pixel intensity, let's say if it turns out to be 128.7467, so dropping this is not going to change the quality of the picture. Yes or no? Are you with me on this example? So Srijan, what we are saying is there is a pixel when you take a photo, no, your photo, if you take this is your photo, and every pixel here it is represented using three components, red, green, and blue. And every component, its value ranges from 0 to 255 or something like that. But if you want to construct a grayscale image out of the color image, then you generate a gray pixel by taking a weighted combination of these red, green, and blue components. Like for example, 60% weight to red, and 40% weight to green and 70% weight to blue, and you can vary these combinations. And finally you get, let's say you get this is the value. All I'm saying is, if in this case if you drop the fractional part, it is not going to impact the grace, the picture quality that much. It will just be fine. They wouldn't they may give different images, but they are not perceptible to your eye. Your eye cannot perceive the difference. Yeah. But on the contrary, let's say, if this number represents millions of dollars, and if it is 128 billion dollars, for example. So this is billion dollars. So if it is something like 128.7467 billion dollars, and if you ignore that 7467, what happens? How much money you are going to lose? So when you are dealing, it depends on the context. No, like for example, that change, if that someone gives us that change, then we can stop working for the rest of that life. So yeah, so it makes a difference. Okay, so say depending upon the context, we need to. Some places it makes sense, some places it doesn't make sense. It's perfectly all right. So yeah, that's all with respect to computations actually. Okay, so you have operators, you have precedence, you have no associativity property, and then there is no typecasting and all these things. So sometimes it's useful, sometimes it's not useful. This is the story. So I would like to go back to the picture that we have seen, that white, because before I move further, we want to move on to the next important idea. I want to. So here, when we talk about real world models, I missed one point. What do you represent here? It's very interesting. Like for example, when we are working with a quadratic equation like ax squared plus bx plus c, how do we represent this quadratic equation? What is a suitable computational model or representation structure for this quadratic equation? Just three, ax squared plus bx plus c. What is a suitable representation structure? And we want to find, no, for example, parabola. Why do you want a parabola? Yeah, it depends on what you want to. The question is, what is an appropriate? So if you want to find the roots of, you are trying to write a program to find the roots of a quadratic equation. What will be your representation for the quadratic equation in your program? What will be your representation for the quadratic equation in your program? Yeah, you just need to store the coefficients. We just need three variables, A, B, C, and maybe you may just want to use a float data type for all these three. So, but on the contrary, if you start thinking about the ax square plus bx, how do you store x square? How do you store x or double? Okay, then it becomes a mess. So so the idea that a is a coefficient of x square and b is a coefficient of x, it's all implicit. It's there in your model. So you don't need to worry about it. All right. So similarly, let's take a different example. So let's say if you are working with, you want to work with simultaneous linear equations. 2x plus 3y is equal to 4. 4x minus 5y is equal to 8. Minus 8. So you want to find a solution to this simultaneous linear equation. How can you go about doing that simultaneous linear equation? What is appropriate representation structure for this? So there is this question, so is matrix possible? So matrix directly is not possible, but there's an equivalent thing to it. So you can represent this as 2, 3, 4, 4 minus 5 minus 8. So later on, we study what is called as a 2D array, two-dimensional array. We can use a two-dimensional array to represent this simultaneous linear equation. So like this, given problems in the real world, you need to come up with a suitable representation structure for it. Are you with me here on these two examples? Very basic examples, but they capture the essence that when we are working with a problem, what is appropriate representation structure? Like for example, later on in an advanced course, you will study like how do you represent a map. So you have all the cities in India, and there is a distance between these cities, and you when you use Google Map and you from Hyderabad to Delhi, you want to drive. How do you find the shortest path from Hyderabad to Delhi? So if you want to find it out, there should be a suitable representation structure for the map. And on the top of that representation structure, you need to come up with a problem. You need to come up with an algorithm which finds the shortest path. This problem is not as hard as traveling salesman's problem. It's very simple. So again, it's an important thing. So how do you represent this map? What is a suitable representation structure? What is a suitable data structure? And what kind of, depending upon the question that we want to ask. Like for example, a question could be, what are all the cities which are within 100 kilometers radius of Hyderabad? Right? So how do we answer such a question using that representation structure? Then comes the algorithmic thinking part there. So now let's go back to this particular thing. So this is the basic, no matter which problem we are working with. So we have this thing, we read input, we process input, and we generate output. Like for example, if you are trying to compute the area of a square, so what do you do? So you read, no, you read the area of, so read, what should we read here? We should read radius, and you compute the, like for example, if it is area, you say area is equal to pi r square, and then you want to print area. So this is what we would like to do. So here computation is happening, here input is happening, here output is happening. So when given a problem, you need to have a you need to think, what is that I'm reading? What is it that I should output? And how should I represent the data that I am reading? And what is the kind of computation that I am doing? So these are the questions that you should be asking. So for example, I know this is a very simple problem, but nevertheless, in the other class, I wrote a program. I'll just reuse that program to show you, to highlight this importance. So here, if you see this code, so in this code, you can see that this is the place where we are reading the input. So we are asking prompting the user, could you please enter the radius of the circle? So this is where we are reading, and here we are doing the computation. So actually, we are not worried so much about circumference. So we can delete circumference. And one important thing here is, that the area variable is defined in between. I don't know whether you are aware of C89 versus C99. Did Jiaul discussed about this C89 versus C99? Okay. So there are two multiple C standards. In C89, you are not supposed to declare variables in between, but in C99, you can declare variables in between. Like for example, on line 12, I declared a variable area which is allowed in C99, but it is not allowed in C18. All right. And then finally you output here. That's all. So this is an extremely simple bare bones structure. This is a bare bones program. Are you all with me here? And also, did you study macros? I heard it is discussed in the lab. How about macros? So yeah, there are two ideas here. So let me, yeah. So let me do this. So I will hold on to these two things. Okay, I don't want to digress from the main topic here. In the next class, I will talk about C89 versus C99. So in the next class, I will talk about C89 versus C99 and macros in more detail. But for the time being, all I want you to keep in mind is in this lecture that wherever pi is there, it will be replaced with 3.142. Are you with me here? Wherever pi is there, this will be replaced with 3.142. That's all. We will discuss in detail about macros C89 versus C99 in the next class because I don't want to digress from the main idea of today's lecture. So, just to give an advantage of why macros are useful, in this particular program, where we are using pi at only one place, it's not a big deal. But let's say if you are working in a large program, and if you are using the value of pi in 10 different places, and I use the value of pi as 3.142, and along comes my boss, who is my boss here? Yeah, Sriharsha comes Sriharsha, Shantanu, they are my bosses. They say, you know what, this is 3.142 is wrong. We should be using this value for pi. Then if it is in 10 places, when I go and try to manually change it, I may change it at 4 or 5 places and I may forgot to change it at a few other places. Or at least if many times when you go to industry, you will be working on code which is written by others, so you don't know where all the places they used pi, so you will be changing the value of pi in some places but not in all the places, right? So but if you have a hash defined like this, I change it here and wherever pi is used, it gets changed. Are you with me here on this? Are you Are you all with me on the usage of pi? It's an important point why it is used. Okay, great. So now let's compile this program and see what happens. I'm deliberately not answering some questions which you are raising there, but I will take them up later, maybe in tomorrow's class. So 12.3. So area of circle with radius 12.3 is 475.35. Okay, so this is very simple program. So you could be, but we'll make it interesting. We'll make things interesting. So that's the reason why, but we are taking one step at a time. This is something. Yeah. Now, can you take a look at this program? So in this program, so what is happening here? So this is a program where you read income here, you read cost, and then you check income is greater than or equal to cost. So in flowcharts, this is what is called as a flowchart. In flowchart, when we are doing decision, we use this diamond block. And if it is yes, what we do is uh, what we will do is we will no we get profit and we compute the profit. And if it is no, then if income is less than cost, then it's a loss. We compute the loss, we print loss, and we come out, right? So a generic picture for this is, so you start here, you somewhere you start, and then you kind of read no, read something, and so maybe you can do some computations, or but otherwise also, let's say this is there are two possibilities, so yes or no. So there is this condition, and this condition, this is either yes or no, and based on that you do some computation here, and based on that you do some computation here, and then you come back here, and there is something, some other computation you do, finally you end here. So in the earlier code that we have seen, or the programs that you have seen, control is going only, this instruction gets executed, followed by this statement, followed by this statement. So control is going one statement after another. There is no jump of control happening there. But here you are encountering for the first time where, depending upon the condition, this is a profit path. This is an S path or a profit path, and this is a no path or a loss path. So one of these two things will be taken. So this takes us, so now let's see, this is the code for this. So in order to write programs where a control transfer like this is present, we have to use what are called as if statements in our program. Great. So you can, yeah. So we have this accounts.c program. So again, so this is you can see. So here what we are doing is we are so this one, these two statements scanf, so they correspond to this read income, and then so you read the costs. This is what we are doing. And then if income is greater than or equal to 0, this is the profit path. So this is, I want you to pay attention to this, to the syntax of the if statement. The if statement has three parts. If is a keyword, else is a keyword, and this is the condition operation. This is what is called as relational operation, where we are checking if income is greater than or equal to costs. If that is the case, then all the statements within this left flower bracket and right flower bracket, this constitute what is called as the if part of the block. They will be executed. In this case, there is only one statement that will be executed. And then if, let's say, if the condition is false, that is income is strictly less than costs, then the else block will be executed, and the else part contains only one statement, that is it prints loss. And finally, after everything is done, we say printf accounting is done, and we come out of the program. Are you with me here on this program? Are you all with me? So now let's run this program and see what happens. Let's run this program. And so GCC accounts.c. So income is 12, costs are 230. Then you say that this is loss. But if it's other way around, 230, 12, you say it's profit, and you get. So if statement is an important thing for you to learn, because it permits us to change, it's a control transfer instruction. Like it permits us to take either one path, either true path or if path, versus the else path or the false path. All right. So if you're all with me here, then let's go to the next uh, flowchart, which is very interesting. Um yeah. So here is very cool stuff. So it takes the game to the next level. So you start here and then you kind of do some computation. You want to take some decision, and if the decision is yes, you come out. If the decision is no, you go back and repeat that step. The fundamental thing in computation is what makes computers powerful is their ability to repeat the same task again and again and again and again and again. So that's where loops come into picture. Loops permit repetition. Repetitive tasks is what computers are really good at. So this is so now let's see how this gets translated. This idea gets translated. This how we can write a code which is very similar to this flowchart here. So now what we want to do is we want to go back. Uh, we would like to uh, take our program, this area program, and we want to ask the user, what is the, do you want to, so here, if you see, pay attention to this code. So, so here, so this is, we are asking the user for the radius, step 1, and then we want to compute the area, and then we are printing the area. This is what we are doing before. But now we are introducing a new element. We are asking the user, hey, do you want to compute the area of one more circle? And if he answers 0, then that means we don't continue. But if he answers 1, then what we will do is we will continue. So here we are reading the flag, and if flag is equal to 1, then we are saying go to the statement which is labeled L1. So the statement, so L1 is attached to the printf statement. So what happens is when the control hits this go to L1 statement, then control will go back to this point. So like this, what happens is you take the area radius, compute the area, you print the area, and you ask the user, hey, you want to continue? And if he says yes, then yes, how does he say yes? He by picking 1. Then if flag is equal to 1, remember in this, this is a new relational operator. The relational operator earlier that we have seen is greater than or equal to, but right now this is double equal to, which checks whether flag is equal to 1. And this if statement doesn't have the else part, it has only if part. So if this is true, the if part will be executed. And if it's not true, the if part wouldn't execute, and the control will go back here. So, and what this go to statement is saying is go to the statement which is labeled L1. So you go back to the beginning. Are you all with me on this program? Does it make sense? So is L1, it's not a method, it is just a label. L1 is, no, we can use anything. We can use begin, go to begin, for example. Anything. Yeah. So now if I say your income, that 20, no, this should not be the case. That is the area is the program. GCC label.c dot a dot out. So now it asks, do you want to compute the area of one more circle? I'll press 1. And then 12.3. And then again it asks. And then I press 0. You come out of the program. Are you all happy with this program? Does it make sense? So if you understood this program, then your programming course is over. Okay, your programming course is over in the sense this is all, everything else is kind of, butter masala and whatever more, but this is that's it. What we have discussed in today's class, that's all you have to know in any programming language pretty much. We looked at the core of programming in today's lecture, and everything else that we see is just like kind of putting more stuff to it, that's all. Any program that is out there, you will be able to solve just by using these constructs that we have seen in today's class. So from my perspective, so if you understood this label.c program, then that means it's an important milestone for you in this course. It's an important milestone for you in this course. What I will do today is I will release one small problem, two, three small problems for you, where I want you to solve those problems using the GOTO statement, not use any other loops, nothing else, only using the GOTO statement I want you to solve. And that gives you some feel for how it works. Does that sound all right to you? Okay. So now I think we should conclude here. This is the right place to stop. Uh, so this begin on line 10, it doesn't matter. It can be anything. It doesn't matter. I will post it in your no, mailing list. In your group, I will post. Anjali, that's a different problem you're having. I have another, let me stop sharing, stop recording.